Welcome to my project bazaar.com. Non-parametric statistics based crowd density estimation. Crowd dynamic management research has been significant attention in recent years in research industry in an attempt to improve the safety level of and management of large scale events and large scale public places such as stadium, theatre, railway stations and subway and other places where high flow of people at high densities is expected. Failures to detect crowd behavior at the right time cloud lead to unnecessary injuries and fatalities. Over the past decades, there have been many incidents of crowd which cause major injuries of fatalities and lead to physical damages. Examples of crowd disasters occurred in past decades include the tragedy of Hillsborough football stadium at Selfridge, where at least 93 football supporters have been killed and 400 injuries in 1989 in Britain's worst ever sporting disaster. Recently in Cambodia, the same incident is occurred, but in a simulation with real-time crowd characterization, such as the estimation of real-time density in order to provide accurate prognosis in crowd behavior and enhance the crowd management and safety, particularly in mega events such as the Gaji. This paper addresses the use of novel sensory technology in order to estimate the people's dynamic sensory during one of the Haji activities. The ultimate goal is that real-time accurate estimate on the density in different areas and provide more accurate prediction of crowd dynamics. This paper investigates the use of infrared and visual cameras supported by auxiliary sensors and artificial intelligence to evaluate the accuracy in estimating crowd density in an open space during Muslims' pilgrims to Makkah. This is the flowchart of our process. In this process, we have to take input video for to crowd estimate the crowd density. Input take us the crowd audio video, and to process the edge detection process to obtain the input video, and then to obtain the histogram equalization for clearly to normalize the input video to estimate the density of the input video. Then we have to take the foreground image frames and background frames, and then finally we have to subtract the both frames or foreground and background frames. The final result of that foreground and background frames to give the estimation of density is to be occurred in final pixel counting. In pixel counting values is take output values for estimate the density of crowd. Those pixel counting values is very helpful to estimate the density of crowd. When a large amount of density is occurred in video, we have to easily counting the pixels from to estimate the density easily. The process of edge detection and histogram equalization is very helpful to subtract the frames of foreground and background, and also counting the pixels for estimate the density of the input video. The ultimate goal is that real-time accurate estimate on an intensity in different areas within the crowd could help to improve the decision-making process and provide more accurate prediction of crowd dynamics. This is main window of our MATLAB process. In MATLAB process, we have to select the current folder in that window, that is common window, that is workspace. The workspaces have the variables to be handled in our process. We have to current folder. In that current folder, we have to files to be added from the source code folder. In the source code folder, we have taken the three input videos, 1, 2, 3. We take 3 input in that process. The main.yum is the main file of our process. The main.yum to be right click. Then right click after we have to select the run or press the F9 button. Click the run button, and we have to display for choosing the three videos of our process, 1 2 3, like that. 1 2 3, in 1 2 3 we have to select the third video for our process as input. That frames have the input, frames folders have the input images for to be for video loaded in our process. We have to select the third video now. Click open. Immediately we have to shows the frames to be in that video. That frames are like edge detection and crowd density estimation to throw the histogram equalization of each frame. Each frame is converted from video as following method. In this method we have to first calculate the edge detection. For edge detection we have to calculate the input frames to grayscale frame. The grayscale frame is handled to edge detection, and then finally the edge detected frames is to be handled for the converted to the frames and to estimate the density from to subtract the foreground frame to background frame. In the subtraction of foreground to background from, we have to calculate the pixel counting. The pixel counting is very helpful to estimate the density of input crowd video. That crowd video is have to the values of very low density, medium density, high density, and very high density. That density is to be have the values of frames. That frames are handled than the very high density is handled than in this process. That those are values of very high density, and then this is a high density. The density estimated to be the process of the pixel counting. Pixel counting is very helpful to the count the white pixel of the video. That is the low density. That's the values of the low density. That's a very low density. The very low density is should be have the only one value. This is the edge image of our process. This is a histogram equalization of our process. This is the background image. This is the background image. This is the foreground image. This is the edge image. This is for the output of our process. Now we conclude the process of non-parametric crowd density estimation. This paper has investigated crowd density mapping using novel sensory fusion model of infrared and visual data combined with artificial intelligence system to estimate the crowd's density of Hodge activities. In comparison with the separate applications of visual infrared system, the result proves that the sensor fusion can significantly enhance the distance estimation of crowd, which will help in the design of safety system for crowd monitoring management. The sensory fusion model is associated with additional sensory and computer cost. However, with the continuous reduction cost of sensor and computer technology in recent years, this is expected to make the sensory fusion system more common, particularly in intelligent building applications. The uniqueness of sensing the fusion model is the expected reliability to function in dark light conditions at different levels, including smoke interference, which makes it useful in emergency situations where power loss, thick smoke can affect visibility. This is the simulation result of 5 levels of density estimation in very low, medium, high, very high, the situations of crowd density estimation. Thank you.